Okay, so we are going to revisit stoichiometry, this time involving gas at non-STP conditions. As you see from letter A, I'm going to skip over STP conditions because we already talked about that in your stoichiometry unit when we talked about using 1 mole equals 22.4 liters. So anytime they mention STP, you know you can use that. However, when they do not mention STP, then we're talking about when a gas is collected under non-standard conditions. So you're either going to use stoichiometry first and then the ideal gas law, or the ideal gas law and then stoichiometry. Depending on what you're given, you will need to figure that sequence out. But regardless, you will always need a balanced chemical equation. So that must be written. So we're going to look at a couple of example problems to see how you're going to be able to figure that out. So again, either you're going to be using the ideal gas law, then stoich, or stoich, and then the ideal gas law. So, our first sample problem. How much pressure would be exerted by a gas produced from 10.5 grams of magnesium reacting with an excess of hydrochloric acid if it's collected at 35 degrees Celsius in a rigid 5.0 liter container? That was supposed to be 35 degrees Celsius. So we first have to write a balanced chemical equation. We have magnesium with hydrochloric acid. Hopefully you recognize that as single replacement. Magnesium is going to kick out hydrogen and form magnesium chloride and hydrogen gas. Balancing it easily. There we go. And the only gas here is our hydrogen gas. So when they talk about how much pressure would be exerted by a gas, that's what we're talking about. We're focusing on our hydrogen. So when they talk about our 35 degrees Celsius in a 5.0 liter container and they ask for the pressure, that's what we're looking at. So that's our T, our V, and our pressure. Looks like we're just missing our N. Our R we need to use, since they asked for pressure in kPa, we would need to use 8.31. So in order to find pressure, we'd need N, which is moles. We can't find that, so we are going to need to use stoichiometry first to get moles. Then we'll use our ideal gas law next. That means we're going to start with our given, which is 10.5 grams of magnesium, and we're going to figure out our moles of our gas, which is hydrogen. 10.5 grams of magnesium. I think magnesium is 24.31 grams according to the periodic table for every 1 mole. Mole ratio is next. For every 1 mole of magnesium, we're going to make 1 mole of our gas. In this case, our gas is hydrogen. When we do this, break out our handy-dandy calculators, we get 0.432 moles of our hydrogen. So that's now the missing piece in our puzzle. So we can go back and use our ideal gas law now. PV equals nRT. P is our unknown. V is 5.0 liters, and remember, liters is good. We're okay with that. Our N is 0.432 moles. R is 8.31. We're picking that value because they want the pressure in kPa. And temperature has to be in Kelvin, so we have to add our 273. Some of you messed that up on your quiz. Remember, we add 273, and that would be 308 Kelvin when we add our 273 here. So 308 Kelvin. When we solve for pressure, we multiply everything on the right, divide by our 5.0 liters, and we get our answer, which would be 221 kilopascals. And that would be our answer. All right, looking at our next one. Ooh, almost made a boo-boo there. How many grams of calcium carbonate would need to decompose? So we're decomposing calcium carbonate. That's a metallic carbonate. If you remember from your special cases, decomposes into metallic oxides and, oops, that was a bad one, carbon dioxide. It's already balanced. Our gas here is our carbon dioxide. We know the temperature is 20 degrees Celsius. We know its volume is 500 milliliters, but I'm going to go ahead and write that in liters because I know it has to be in liters. The pressure of it is 0.950 atmospheres. And they're asking us for the grams of our calcium carbonate. There's no way we can do stoichiometry first here, because to do stoichiometry, we'd have to know our grams. So we have P, V, and T already given to us. We know R we would use for atmospheres is 0.0821. So we have everything here available to solve for N. So we can use, in this case, the ideal gas law first to get us moles. Then we're going to use stoichiometry. So we're going to use our ideal gas law first. PV equals nRT. P is 0.950 atmospheres. V, we said we're going to change it because it has to be in liters. N is what we're solving for. R, we chose 0.0821. And T, we got to add 273 to make it 293K. Remember, it's always have to be in Kelvin. My dog's decided to fight in the background now. And N becomes 0.0197 moles of our gas, which is CO2. But they don't want CO2, they want the CaCO3. So we have to do some stoichiometry now. 0.0197 moles of CO2. And we're going to do our stoichiometry. For every 1 mole of CO2, according to this, it's a 1-to-1 mole ratio, is 1 mole of CaCO3. But they don't want moles, they want grams, so we need to do a molar mass calculation. And according to my calculations, 1 calcium, 1 carbon, and 3 oxygen is 100.09 grams. I wish we were in class so I could make one of you do my molar mass calculations. And I get 1.97 grams of there goes my dogs fighting again, calcium carbonate. All right, so again, take the time to figure out whether you're doing ideal first, then stoich, or stoich and then ideal. So look at what you're given, figure out who your gas is, and ask questions if you're stuck. Talk to you later.